just a few people entered now. Okay. Hello, everybody. Welcome to a new episode of our seminar series on machine learning security. I'm Maura Pintor, and I'm assistant professor at the University of Cagliari. I want to share a few things about the seminar before we start, and then we will listen to this amazing talk by Scott Coull. First of all, the event is live streamed and recorded, so if you don't want to be recorded, you can follow us from the YouTube stream. For the questions, you can ask questions directly in the Zoom call. Please wait for the end of the talk, or also by typing in the chat. Otherwise, we will also occasionally look at the YouTube comments. Follow us on Twitter, LinkedIn, or Eventbrite, or also the website. We will share the links in the chat very soon to receive updates on the new events we organize. And then finally, if you want to know more about machine learning security, or you want to strengthen your background, you can find a free course in the same YouTube channel where we are live streaming right now. I want to thank all people who helped me organize these seminars. And now I will give the stage to Luca, who will present our guest for today.
Thank you, Maura. So today I'm very, very glad to introduce you to Scott Coull, which is head of the data science research at Google Cloud Security, where he leads a team of talented data scientists in applying cutting-edge machine learning techniques to solve complex computer and network security problems. Over the course of his 20 years career, his research interests have spanned a range of topics, including malware classification, censorship circumvention, network traffic analysis, data privacy, and applied cryptography. Most recently, he and his team have begun exploring ways to more tightly couple cybersecurity subject matter expertise with machine learning technology through the application of weakly supervised learning and large language models. Dr. Coull received his PhD in computer science from Johns Hopkins University and completed his NSF CRA Computing Innovation Fellowship at the University of North Carolina at Chapel Hill. Thank you again for coming at this event. Really, thank you. The stage is all yours.
Great. Thank you very much for that, that great introduction. And thank you, everybody, for joining me here. Hopefully, everybody, can someone just, I can't, now that it's in presenter mode, can someone just clarify they can see the slide deck?
Sure, yes.
Cool. Well, thank you all for joining. Yeah, to get started here, you know, as with any work, we want to always start with the people who actually did the hard parts. So I want to, you know, acknowledge my coworkers, Ethan and David, who are both on my team at Google and Mandiant. Daniel Olszewski, who's one of our former interns from the University of Florida. And then Edward Raff and James Holt, who were our collaborators from the Laboratory for Physical Sciences. So I want to start a little bit about me, right? Because I think there's something that I want to try to get to in this talk, which hopefully this will help set up a little bit. So like Luca said, you know, I've been in cybersecurity research for quite a while now. Really worked on a bunch of different stuff. One of the things that excites me the most, though, I think, is being able to explore problems that are the intersection of research and practice. So basically places where, you know, the assumptions that are being made by research, or maybe the problems that are being explored by research, are not necessarily well aligned with what's happening in practice. I think there's a really interesting and valuable bunch of problems there that are really kind of undervalued by both communities, honestly, in some cases. And I think that's also where, you know, the real world impact can really get driven from. So a lot of the stuff I say here is going to be based on my experience having created MalwareGuard. So MalwareGuard is a static analysis based machine learning model for malware classification that we deployed at FireEye, and then, you know, FireEye became Mandiant, and now it's at Google. So that currently runs on, I think, somewhere around 2 million or more endpoints every day, scans tens of thousands of mailboxes, it's on thousands of different network devices, et cetera. So a couple of objectives. So first thing is, I want to share a little bit some of these practical considerations when we're applying ML to malware analysis tasks. I also want to discuss a little bit about how we can use metric embeddings to solve multiple downstream problems, right? And then finally, the final objective I want to get through is I want to present our particular approach to helping reduce technical debt from managing multiple ML models in the case of malware analysis tasks. So hopefully we'll get through all three of these. You'll find something valuable for each of these in this presentation. So here's a little bit of a sort of pathway for where we're going to be going during this talk. We're going to start here through some introductory stuff through malware analysis and pipelines that most real world malware analysis companies have to deal with. We'll go into metric embeddings and how we're thinking about using that to solve some of the problems that we're going to talk through. We'll talk through our evaluation results that we have on a couple different data sets. And then finally, we'll end with some takeaways and other high-level findings. So hopefully this will be a really interesting talk for some folks. There's hopefully a little bit of something in there for people who are a little bit on the research side to get some knowledge on the things that happen in practice. Hopefully for folks that are on the more practical side, there's some interesting research tidbits on things to explore. So here to start with, I wanted to go through kind of like at least what my view of malware analysis in the real world kind of looks like. If you kind of look at the literature today, I think what you'll find is that the vast majority of papers that are coming out in the malware space have some detection angle on it, right? It's how well can you detect Android malware? How well can you detect Windows PE files that are malware? Maybe there's occasionally a paper that tries to combine that with some sort of family classification, right? Your malware family. And I wanted to take a moment here to just kind of like point out that in fact, like the world is much larger, much larger than this one area. Now it makes sense why people, focus so much on detection, right? There's clear data sets out there. There's obvious benchmarks. It's really easy to determine when you've sort of won, right? Like when you've done better than previous work, because it's all quantifiable in that way. But when it comes to like reality, the detection part is actually only one piece of the problem. It's a very important piece, but it's only one piece of the overarching problem. So I wanted to kind of walk through this cycle here really quickly with everybody. So the first thing to point out is that detection isn't even the first step in sort of the data analysis or malware analysis pipeline. Actually, the very first step is actually like data sampling, because out there you have a huge number of samples, tons of repeated or near duplicate examples that are out there. Out of hundreds of thousands of samples that, let's say, VirusTotal would get on a daily basis for like Windows PE files, only a tiny fraction of those are really and truly like unique, interesting, novel in a way that a machine learning model is learning something new rather than just building in additional bias to data it already has. So the very first thing that we end up doing in almost all cases is sampling down the data in some sort of stratified manner based on different types of representations or understandings of the data, so that we want to get a nice uniform, good representation of that sample space, right? So we're not unduly biasing the model towards specific types of malware. Then you come to detection, right? And detection is really interesting because it happens all over the place. You have detection that happens on the endpoint, right? So on a person's machine, which just naturally requires you to be potentially a little bit more thoughtful about how you tune your false positive and false negative rates, right? You don't want to, have to have someone, rescue something that they got quarantined every time they open a Word doc or something like that. But then you also have, cloud-based technologies that are also in play here. So actually, this particular sort of slice is actually pretty deep when you think about it. I'll get back to that at the end of the slide, but you can kind of actually think about a lot of different steps that happen, and even in that detection space. Then, like, let's say a malware was actually detected. This actually has to get escalated to a security engineer somewhere, right? They have to understand what exactly was detected to know how to remediate it. And so if all you did was just say, hey, this file is bad, you're actually giving the malware analyst or even the security engineer very little information to work on to actually fix that problem. So you have to provide some kind of additional data or metadata for them to base their decisions on. And one way you do that is by doing additional classification tasks after the detection. So for instance, family classification is a very common one, especially if it's a known sample that's previously been observed. Type classification is another one that's very popular, where you try to actually figure out different capabilities that the malware has. So for instance, like Microsoft in their naming oftentimes puts things like Trojan or dropper, basically things that capture the type or capabilities of the malware in some way, or what it's actually doing. And that's really important because that's what the security engineer is going to key in on. And then you kind of have this like final step that I have here, which is actually retrieving new samples, right? So sure, you can get lots of samples from different industry sources and whatnot, but at the end of the day, for like truly unique, especially long tail sort of things, when you think about goodware has an amazingly long tail of things that people are creating every day. That's just goodware that you would have never observed or seen because it's only available to this particular organization or customer. So eventually you're going to want to have to be able to pull back some of these samples. In order to do that, well, one, you have to make sure that it's actually in fact novel, right? So that goes back to the data sampling question. But then also you want it to be efficient. You don't want to necessarily, a lot of customers don't necessarily want you to be pulling back full binaries because that might include their intellectual property or other information that's not great. But you have to balance these things. So there's all these different sort of slightly separate problems that need to be solved. And as I said, just sort of this last point is that this is sort of what I describe in my mind as like the high level sort of tasks that need to be accomplished. But even within these, there are increasing levels of complexity, right? So I mentioned detection. For something like detection, you might have signatures that need to be managed on the endpoint. Maybe a static analysis classifier that happens on the endpoint. Maybe dynamic analysis that gets that happens in the cloud after a sample is shipped off into the cloud to get analyzed. Maybe there's behavioral analysis that happens afterwards as well, right? So hopefully you're getting the sense here that like in order to really get a full, robust, holistic malware pipeline, you really have to have a lot of machine learning models, maybe too many machine learning models, depending on the way that you're architecting everything. So there's a really awesome paper. This is actually a number of years old. I think this is from maybe NeurIPS 2014. Number of years ago, but I think all the things it says are 100% still truthful today. Machine learning pipelines incur significant technical debt, right? And all you have to do is just think about how much effort it takes to curate a data set, make sure that you clean it appropriately, develop features and maintain those features, implement pipelines to automatically extract and maintain features, do the training, do monitoring on it. All of those steps need to be done for every single model that you're deploying in this analysis pipeline. So hopefully you can get the sense here, just sort of intuitively, that having, let's say 5, 6, 7, 8 different models is an incredible amount of work to maintain over the long term. And some of these might even have totally different feature sets from each other, right? Which totally makes it even harder, right? If you're making a slightly different feature set for your type classifier, maybe based on disassembly information versus your static classifier, well, now you also have 2 different feature extraction code bases that you also have to be considering. Then you also have this kind of interesting thing, right? Like there's dependencies between these models, as you might imagine, right? Depending on what exactly gets selected as malware, that obviously impacts the the distribution of what's being shown as input to a family or type classifier, or what's being sampled during the clustering operations. So there's all these sort of like natural dependencies, and obviously drift from one model is going to affect other subsequent models in this pipeline, right? Adding even more sort of what I would describe as technical debt to this whole process. And these do have real actual costs to them, right? There's costs in terms of serving them, there's costs in terms of running all these pipelines. And obviously there's just like the human effort that goes into maintaining all these things and keeping them working well as a holistic system. Okay, so hopefully with all that, you kind of got an understanding here a little bit of some of the complexities of real world pipelines in the malware analysis space. What I want to pivot to next is talking a little bit about metric embeddings. So we're thinking about like, how exactly do we make this a little bit easier for ourselves, right? What techniques could we use? What approaches could we throw at this problem to make this more manageable in some way? And what we'll talk about in the next section is exactly how we're going to use metric embeddings to try to solve those problems. So for those that don't know, metric learning, I won't go into like extreme detail here just for lack of time, but for those that might not be aware, right, metric learning is basically trying to teach a deep neural net to learn a distance function, right? A function that somehow maps objects into an embedding space where somehow the locality in that space captures similarity, for some definition of similarity, of other objects around that one, right? What's really interesting about these, as we'll talk about later on, is that there's lots of interesting ways in which you can kind of imbue or kind of push interesting and complex information or semantics into these spaces in a way that maybe the originating feature space that you're basing the metric embedding on may not actually be able to capture all by itself. So how do we achieve this? So this is just sort of a very high level walkthrough of this process. I thought this was an amazing diagram. It's from a survey, deep learning metric survey, deep metric learning survey that's linked here at the bottom. But I think this is a really interesting and really illustrative kind of sort of graphic to kind of walk through. So, you know, you start with an object, right? So objects in our case are going to be binaries. They have some sort of inherent or original input feature representation that come along with them. And the idea here is, and in particular for like a Siamese network, which is what we're going to be focusing on, you know, basically what you're looking at is picking an anchor point. So basically picking a sample of those binaries. And then picking additional objects that are both similar and dissimilar from that anchor point, right? And actually, this is going to be a key concept that we're going to look into later on, which is, you know, in fact, are we getting good representative, similar and dissimilar examples to learn on? So that's actually going to be a key problem that comes up later on. But then what we can do is we can use this sort of Siamese network approach, right, which is shown in this sort of block D on the lower right-hand corner, where basically we have, you know, a single deep learning model, right, single network, single architecture, single set of weights, and we can basically think about them as being copied, right? So it's the same exact network running on both sides of this Siamese architecture. Then you can give your anchor point to one of them. So let's say this orange triangle is the anchor point. So we give it to this network, and it provides an embedding, right? Some sort of lower dimensional representation of what that orange triangle is. We do the same thing, but now with maybe a dissimilar point, this black square. We send that through the same network with the same weights and get another embedding. And then we're going to basically use a distance metric to measure how similar or how different those embeddings are within that embedding space. And there's many different ways of setting distance metrics. Euclidean is what's being shown here on this diagram, but you know, another very popular one is like cosine similarity, Mahalanobis distance I've seen as well. We're going to be focused, like I said, on Siamese networks and contrastive losses. So that's basically looking at individual pairs. There's other ways, of course, of doing this as well, like triplet loss, which uses not just an anchor and a similar or dissimilar point, but an anchor and a similar and a dissimilar point, hence the triplet terminology. But for our case here, we're going to focus on the contrastive loss and Siamese networks. The last thing to note is that in particular for contrastive loss, it's really helpful to often kind of include a margin in your loss. So if you kind of look at the margin formula down here, kind of Y true is kind of your indicator about whether or not the sample that you're measuring at this particular moment is the same or different than your anchor. So Y true would be 1 for if it's the same, and 0 if it's different. And so you can kind of see that in this particular case, there's a margin for negative examples. So basically you want to ensure that, that there's a kind of a minimum amount of separation between yourself, like all the similar objects and the dissimilar objects, right? So you want to ensure that there's at least some separation there so they don't start kind of blending together or end up in other sort of degenerate states that are not really helpful for actually creating the final space. And then the final space, as is shown here in sort of block E, effectively kind of tries to separate, through the use of these losses, these main kind of groups of objects, right, based on their similarity or dissimilarity in their learned representations. So this is what we're going to use. You might be asking a question, okay, well, why embeddings? Maybe this was a couple of months ago, before all the large language model stuff came out. This probably was a more appropriate slide. I feel like everybody and their brother knows why embeddings now, but I think it's useful to just clarify and mention. So why embeddings? Well, first of all, as we talked about in the beginning part, the introduction, we need something that's transferable, right? That's transferable to many different downstream tasks. And inherently, embeddings, in the way that they're used and the way that they're learned, naturally transfer very well to many different tasks, as long as you set up the sort of embedding problem itself appropriately when you're defining the idea of similar and dissimilar. The other thing, as I kind of mentioned in the previous slide, is that you can actually incorporate some really interesting contextual and semantic information into this training process just by virtue of what you're calling similar and dissimilar. I'll talk about very briefly some other results that we have at the very end, but one of the things that we found in some of our work is that you can actually even get these spaces to learn interesting representations that aren't even naturally viable in the input space. So for instance, we got it to learn information about disassembly, like so we used disassembly information to define similar and dissimilar. But then our actual input representation from each of these objects was actually static analysis features. So it was able to map information or signal from the static analysis features into this sort of more rich, semantically rich space based on disassembly. And that kind of goes to my next point here, that it's beyond even what is readily available in that original input representation. And then the final bit here, and this is kind of important from more of the cost standpoint, is that when you do these embeddings, you're oftentimes going from a much larger space to something that's a little bit more compact or low dimensional, and that can help us in a lot of different ways here, right? If we have to retrieve and store a number of different files, from a number of different customers, that's going to naturally amount to a bunch of savings in terms of storage, potentially reduced training time because of the smaller input representation, and many other things. When we're talking about, for instance, our data store is somewhere on like the petabyte range, like the multi-petabyte range, I think at this point. You can easily imagine that being able to go from raw binaries down to a very small, low-dimensional representation, and being able to quickly index into those representations and retrieve them can actually amount to a bunch of savings in both time and money in terms of storage. So on the bottom here is just like a very quick kind of visual representation of kind of the overall process. Basically we start with the raw data, which is these Windows PE file executables in this particular case. We featurize that into some sort of initial input representation. and then give it to an embedding model. That embedding model then projects it into the embedding space. And then we use that actual embedding as effectively the features that we feed into a number of different downstream supervised tasks, like the ones that we saw at the beginning of the presentation, and try to use those effectively as our basically as the individual models for each of those 5 different parts of the malware pipeline we were talking about. So a little bit more detail about our approach in particular, right? So it's trying to move from more general to a little bit more specific about what we did. So our initial attempt here was actually to replicate VirusTotal vhash clustering. So for those who are not familiar, VirusTotal is basically a service where users, customers can upload files and get a number of different vendors to provide determinations or detections on those files. They have, as part of their reports, a really helpful hash called a vhash. Now they describe it as mentioned here as this in-house similarity clustering algorithm that allows you to find similar files. That is all the information that is available about it. And so we found it useful separately in our own work in trying to do different types of sampling. And so we decided to ask the question, well, okay, well, that works well for all the things that we can get VirusTotal reports on, but is it possible for us to create an embedding that will effectively replicate this, right? Not knowing whether or not this is potentially more advanced than other structural hashes that are out there, not knowing exactly where they pull information for this hash from, can we replicate it using this embedding approach? During our training, we initialized this network with our embedding network with the Xavier algorithm, basically randomizing with Gaussian noise all the weights. But then an interesting thing to mention is that we actually have found that it's very important to pre-train the network with goodware malware detection tasks. And we do this with a subset of our training data set that we use for our embeddings. And I mention this in particular because it was one of our interesting findings that, in fact, without the pre-training, without getting the network into sort of a space where it kind of understands or is very close to already this idea of similar or dissimilar, we had a lot of problems getting the network to actually converge during training. So this was sort of like one of those things where, we kind of got inspired by a lot of the work happening out there with transformers and pre-training, realized that we had the data to do this and thought, well, let's see what happens. And in fact, it led to much more stable training after we implemented this. Another thing, which we'll talk about in a little bit, it's very important for us to have good coverage of the space of samples during training. And I alluded to this, I believe, in the last slide or 2 slides ago, where I said, it's very important when you're doing these contrastive methods to be able to expose the model to all sorts of different types of pairing, both similar and dissimilar points. And so that's particularly important here where our data set's actually quite large. We'll talk about this again in a little bit, but with the number of clusters that we're seeing, we basically found out that we had to create a custom batching algorithm in order to make this work out well in terms of training. And we'll talk about that. And then finally, we're going to use, as I mentioned in the earlier slide, we're basically going to use these outputs of the embedding model as the low dimensional feature representation for our downstream models. So again, just looking at this diagram, we basically do this pre-training as step 1 that initializes our network to something that's sane for the task that we're asking it to perform. We use that initialized network to set up a Siamese architecture and begin our contrastive metric learning training. That is learned via the training data set that we have that produces the embedded data. And then that goes to our training where we use sort of more traditional classifiers like GBM and k-nearest neighbor classifiers to do the different transfer tasks. Okay, so a quick dive into the model architecture. I don't think this is anything particularly stunning here. This is a very standard feed-forward neural net kind of architecture. If you look on the right, basically going from top to bottom, we've developed this with the idea that we're going to use as input static analysis features. And in particular, we developed the model you see here based on the 2,381 hand-engineered static analysis features that were presented with the Ember malware dataset. For those that are familiar, Ember is a really great dataset that's out there that contains information about malware and goodware, I think from 2018 and earlier. So really great features involved in this. So information on headers, imports and exports, information on sections and different byte histograms that are in the file, etc. But again, strictly static analysis based features. But you can kind of see as we go from top to bottom, the input here is 2,381 dimensions for our features. We go through several layers of sigmoid, dropout, and batch normalization. And then kind of eventually make our way down to the final linear layer, which gives our output size. So as we'll see when we get to the evaluation results, we actually evaluated a number of different dimensionalities when it comes to the output, 32, 64, 128, and 256. The only other thing I'll mention here very quickly before kind of moving on is sort of like maybe a cautionary tale here on the interaction between activations, right? So those, we chose sigmoid here, but ReLU, ELU, etc. The interaction between those activations, the distance metric that you're actually using in your losses, and your output layer, right? So one of the things that we very quickly found was that if you use certain types of activations, you're effectively throwing away half of the space that your model has to learn in, right? Effectively. And so with our particular distance metric, so we used Euclidean metric, we wanted it to really be able to use the full span of kind of the activation space. And so we went with sigmoid. There are probably other great choices depending on which metric you use. But it was another interesting finding for us, I think, as this being kind of one of our earlier kind of forays into the kind of metric learning space. All right, so I did mention earlier that there was also this idea of a custom batching algorithm, and it's very important because we want to make sure that we get good coverage over all our samples. So one of the particularly interesting things about this data is that there's a huge number of vHash clusters. So of this data set has about 800,000 labeled examples total. Out of the 800,000 examples, there I think are somewhere in the order of 30,000 or more individual clusters available, right, to us. And that doesn't necessarily map to families or anything like that. This is purely like a structural thing. But you find some really interesting things. So first of all, obviously that's a very large number of clusters in terms of if you're thinking about clusters to describe similar and dissimilar groups. The sizes are incredibly highly variable. And again, that kind of makes sense when you think about, something like Emotet, which has, this sort of metamorphic property where it kind of slightly changes itself over time, but maybe not that significantly to be in a different cluster. So hugely different sizes, huge number of clusters. Interestingly, the clusters themselves actually don't map to goodware and malware kind of by themselves. So in fact, you'll find many clusters that actually have both goodware and malware in the same vHash cluster itself. So clearly, kind of with all this taken into account, just randomly sampling from this space of 800,000 samples to try to get your pairs is just not going to work well, right? And that's exactly what we found, that you just won't get enough signal that's useful to be able to get that separation and to get the model to really learn similar and dissimilar in a useful way. So what we ended up doing here was creating this custom batching algorithm. And it's really not that complicated. It just ensures that we get good coverage over all the clusters. So what we do here is the first thing we do, if you're following along with the image on the right, first thing we do is we split the cluster into basically subclusters or subsets. So we have like cluster 1 goodware and cluster 1 malware, and so on and so forth for all our clusters. We sample C clusters, so some number of clusters, C being kind of a hyperparameter here. We sample them without replacement to kind of create the clusters that we want to have in our batch that are going to be compared to each other. And then from each of those clusters, we're going to sample M individual samples. So altogether, the M samples from all those clusters are going to make up one batch for us as we train. And we're going to basically define an epoch for us as going through all of those clusters that are available. So once we basically exhaust going through all the clusters, we call it one epoch, and then we start again and again randomize the combination of C clusters that we're creating and so on and so forth. So hopefully you can get a kind of an intuition about why this would be useful, right? So we're getting, first of all, we're ensuring that there's really good exposure and sort of comparison among different examples within the different clusters, but then also ensuring good uniform kind of representation across all the clusters. So, you know, if we have a huge cluster that has thousands and thousands of samples in it and a different cluster that only has a handful, you know, we're not sort of biasing towards that large cluster and not doing well on the small cluster. And this is actually something that's going to be going to come up in a little bit when we talk about metrics, which is that you kind of got to think about which metrics are going to ensure that you're not biasing some of your numbers towards those larger clusters. But we'll talk about that in the evaluation section a little bit. All right, so evaluation. So that kind of covers all the main topics of kind of what we worked on, why we worked on it, and kind of some of the interesting findings that we had as we were developing the process. What I want to do now is kind of talk through the evaluation we did, or at least one of the evaluations we did. I want to talk through how they map into those different tasks that we talked about at the beginning of the talk. And then I want to spend just a little bit of time going through some additional results that we have that maybe don't quite as easily fall into the flow of this talk, but I think are still really interesting to talk about anyway. So in terms of experiment, as I already kind of alluded to, we're using Ember 2018 dataset. That's a dataset of 800,000 goodware and malware binaries, Windows PE files. Mentioned already the hand-engineered static analysis features that we use. These come labeled, so we have a nice split of about 400 goodware and 400 malware each. Those are themselves subdivided into test and training sets. Training set is 300,000 each, and then the test set is 100,000 each. So that gives us sort of our malware goodware task labels. For the family classification task that we mentioned earlier, we have AV class labels. So for those that aren't aware, AV class is a really nice tool. I believe there's now a new version of it out that does even better. That basically takes in a whole bunch of vendor signatures and is able to provide a family name and other metadata about the binary or the malware. So that gives us the labels for the family classification task. And then finally, we have the type label, which is we extracted basically directly from Microsoft family names. And again, as I said before, these are things like dropper, Trojan. I'm trying to remember other ones off the top of my head, but hopefully you get a flavor for what the type labels kind of look like here. They're kind of capturing that capabilities kind of idea. And then finally, as our sort of similarity and dissimilarity signal that we used in our contrastive training, we use that vhash cluster assignment. Basically, if you're in the same cluster, you're similar. If you're in a different cluster, you're dissimilar. In terms of training for the embedding network itself, we use vanilla SGD with a learning rate as shown here. We've set a max of 100 epochs. We also had an early stopping criterion based on training loss. You know, anecdotally, these usually converged within 30 to 40 epochs. Very rarely did it go beyond that. So fairly well-behaved training, especially after we did the pre-training that I mentioned earlier. One thing I'll note, which we'll see in the results, is that we actually considered 2 different settings when we were doing training here. So having seen kind of the benefit of doing at least some supervised task in the pre-training, like in terms of setting up the model weights, we decided to experiment a little bit with both single objective, right? So just the vanilla contrastive loss with a Euclidean distance as our metric. And then also a multi-objective case where we basically take that same contrastive loss, same metric, and then also added in a like a cross entropy loss for goodware and malware classification tasks. Now, in the past and in other literature, multi-objective learning has been very, very useful in providing kind of like more robust representations for malware. And so we thought this was a really interesting thing to examine. And so we'll see how that does in our evaluation results in a second. And then finally, for our transfer model training, we have basically 2 different models that we use for the different tasks. We have light GVM with 1,000 trees, which we use for the malware detection task, and then a k-nearest neighbor approach for the multi-class family and type classification. We actually also did try light GBM, but light GBM is just not inherently not quite as good at those high cardinality classification tasks. KNN also kind of, I think, used the embedding space a little bit more than the light GBM model did. So we ended up going with k-nearest neighbor for those multi-class tasks. All right, so let's get into some results here. So on the right here, you'll see basically a t-SNE plot of the top, I believe it's the top 12. I have to count it again, but I believe it's the top 12 largest vhash clusters projected from the embedding space. So as you can see, right, like qualitatively, this did pretty good, especially for these larger groups. You will see that like as you get to like very, very low number groups, like the performance degrades slightly, but it's actually still pretty decent given the the massive imbalance in the originating data in terms of sizes of the vhash clusters and so on. And so we have some really interesting, seemingly some really interesting embedding space or information put into this embedding space. So the other way that we looked at sort of clustering performance is using a metric called mean average precision at R. I won't go into the details of this. It's actually a little bit of like a very nuanced thing. So probably people have heard of mean average precision, particularly in different types of like image detection or classification tasks or retrieval tasks. You may have also heard of R precision, which is similar. Basically, the gist of why we chose this is that is kind of going back to what we said about this, hugely imbalanced set of how many samples are in each cluster. So, basically, just by pure luck, if we were to do, let's say, mean average precision at an arbitrary K, right? Let's say K being 10, top 10 retrievals from this space, you would kind of just as a large cluster, by pure chance, you're more likely to get high precision scores for that case, right? Whereas very small clusters are going to have kind of a harder opportunity to get good scores. So in order to give us a more realistic view on this, we use mean precision at R. And really the difference here is that instead of just setting an arbitrary K, what we do is we let each cluster define its own radius or R that the number of samples that it'll retrieve. And basically what that does is it kind of almost think about that as normalizing to the size of the cluster. So if you have a really large cluster, your R is going to be very large, and you basically have a higher bar to being able to do well there because you would have to fill out all of that top R examples to get a very high precision score. So for our map at R numbers, they were all around about 50%, which is actually quite good for such a pessimistic metric. Basically, that means that on average here, of the of all of the possible test set examples, 50% of them were in the top of whatever the retrieval was for a given sample from each cluster. So that actually looks pretty good in terms of clustering performance. So that kind of checks one of our boxes in terms of our pipeline, right? Another thing that we wanted to do is, in addition to clustering and being able to sample from those clusters for data sampling and for retrieval, we also wanted to be able to do malware detection. And so again, we have our t-SNE plot in the bottom right. Again, qualitatively shows some pretty good separation. There's obviously a lot of there's kind of an obvious global separation here, but then if you kind of really zoom into some of these spots, you'll see there's actually pretty good local separation as well. Obviously, it's not perfect, but in a lot of cases, there's actually pretty decent separation. So qualitatively, we again look like we're in a pretty good space. On the top, on the right-hand side, we have basically a chart showing the AU ROC, the area under the receiver operator characteristic curve, showing how well both the single objective model using only contrastive learning and the multi-objective model using both contrastive and cross-entropy losses are doing in this case. So there's a couple of interesting tidbits that I'll just point out quickly before moving on. So one, the single objective model has this kind of really nice behavior where as we continue to increase dimensionality, you do still you continue to see sort of marginal increases in performance. It's also got relatively well-behaved variance there, which is nice to see. Multi-objective, on the other case, clearly outperforms us here, which you kind of intuitively imagine because you're kind of training on a malware detection task. So, you'd imagine this would naturally be pretty good at malware detection, but doesn't really have quite as nice a behavior, especially at the top level of the higher dimensionality for the output. One thing to note here, obviously, is that this versus just the static light GBM model is not as good, right? We lost basically a percentage point or so in our performance by going to this embedding approach. Okay, moving on to family classification, same kind of ideas. Again, bottom right is our t-SNE plot of that space with respect to, I believe, again, like the top 10 or top 12 malware families. Again, you see pretty good separation. You see the model kind of doing its work and making nice sort of separable bubbles around different areas. On the top right, you see, again, in this case, the accuracy for the family task. This is, again, a multi-class task. I forget exactly how many families there are, but it's in the tens, high tens probably. And so, this is actually quite good, I think, accuracy score for that type of task. A couple interesting things, again, are, in this case, both single and multi-objective models are actually behaving pretty well in terms of its performance variance. Multi-objective again wins, but this is actually kind of more interesting, right? Because we trained it on the malware detection binary task using cross-entropy as part of its multi-objective loss. But here, we're actually doing better, not just better than the single objective, but actually better than the baseline model for a totally different family-oriented classification task. So really interesting kind of result here. And then we go over to malware type, and we see actually a very similar behavior, right? Pretty well-behaved variance in terms of performance, and clear kind of improvement in performance over both the baselines. In this case, we show both the k-nearest neighbor and the light GBM baseline. But clear improvement over both baselines by using the multi-objective embeddings versus just the static features themselves, or versus the single objective embedding. All right, so a couple of very quick notable results that I want to talk through, and then we'll wrap up. So one, we did do a couple of interesting experiments where we swapped out vhash for something called CAPA. So CAPA is a utility released by Mandiant, basically uses disassembly-based information to determine different capabilities about a binary. So whether or not it makes network calls, et cetera. And in fact, we were able to replicate this very, very closely using only, again, the input of static analysis features. So really interesting kind of finding there where we were able to get kind of this embedding space to learn more complex information. The other, upside there is that we didn't really see, we saw a slight improvement, but not really a major improvement in terms of transfer task performance. We also tried a more interesting kind of approach in terms of trying to break down the learning into more fine-grained information. So contrastive learning is a very coarse loss. We looked at using Spearman rank correlation coefficient as an alternative or as an adjunct or alternative to that more coarse contrastive loss. Basically, this allowed us to kind of like optimize for whether or not we're able to get like fine-grained rankings of similarity across different examples. And here we found another kind of interesting thing, which is that by itself, Spearman was terrible, performed very poorly, which I guess you can kind of imagine because it's so fine-grained, you probably aren't able to really get enough kind of depth of signal to really learn anything. But when combined with our contrastive loss, actually improved overall performance again. So really interesting stuff there. And then the final thing, we did do a couple of adversarial robustness examples, kind of experiments. We use, just for sake of simplicity, black box approaches so that we can do full end-to-end type of attacks. So we use actually Luca's Gamma framework and applied a couple of attacks that were available there. And again, saw some pretty interesting stuff. We actually saw in some cases, the embeddings improved robustness over like a baseline of like GBM. And in other cases, it absolutely tanked it, like dropped off the map, must have opened up some huge robustness hole. So again, really interesting stuff that we found there. Won't talk about it in too much more detail, but just to let you all know that there's some other stuff to dive into. So finally, for the summary, I want to just kind of talk through and review a few things that we reviewed and talked through today. So first of all, performance on downstream tasks. I mean, basically what we saw was that the embedding-based approaches were at least competitive, right, in the same ballpark, or better than the baselines were using the static features alone. And we've also found, both via our CAPA analysis that I was just talking about, as well as kind of being able to embed information about these V hashes, that it also captures some sort of complex semantic concept in this embedding space that can be very useful for data set sampling and other clustering tasks. In terms of the tech debt, like the actual problem that we wanted to solve, right? So if we're talking about like a 32-dimensional feature, versus, let's say, the 2,381 dimensions of Ember, you're talking about a 98% reduction in storage costs to store the embedding versus the other, or to be able to transfer that from a customer. You also get this sort of nice ability to have a single unified space or a unified pipeline where you basically have to deal with one feature space, one model to retrain that can then feed everything else and potentially, hopefully, lead to less of that sort of technical debt, the dependency and other drift that we might see if we were kind of creating each of these models separately. And then finally, I just wanted to point out some of the interesting quirks, right? We needed to do pre-training to get stable, to get the models to train stably. The multi-objective training was actually a huge performance improvement for us. And then finally, kind of had some of these interesting results from the adversarial robustness cases, showing both improvements and huge drops in robustness. So with that, I'll stop and I'll open it up to any questions that you all might have. Thank you very much for your time.
So really, thank you for the very, very interesting talk. It's question time. So if everybody has a question, either just raise your hand on the, oh, super fast. Professor Lorenzo, you go, you have the stage.
Hi guys. Ciao Luca, Maura, and all the others. Hi Scott.
Hello,
very great talk. There is, of course, there is some confirmation bias on my side. So I'm always fascinated by these type of talks and this type of research. But so take whatever I'm saying with a pinch of salt. With this bias, inevitable bias. So I was wondering, so the results are pretty interesting. Like, I believe that it's a little bit unclear, my feeling is that there's no, it's hard to draw conclusion still at this stage, which is promising anyway. So there are certain things that are actually promising and other things that we don't know, and that's fine. So I had a question so I have several questions, but one question I wanted to perhaps understand a little more is on explainability, whether you believe that, so you reduced feature space a lot. That's great. That's awesome. So I wonder whether, and the embeddings, let's assume that the embeddings capture, I'm not sure whether they capture semantics because, of course, it starts off with, the features that you feed the embeddings with. So they learn something out of that initial input. That's fine. Have you tried to understand whether what you get back is something that analysts might actually work with more easily?
That is a very good question. So we have not tried to do an end-to-end explainability experiment with the embeddings. With that said, right, I think it is certainly possible to do, right, with some of the stuff that is out there. I don't know. I don't want to draw too many like totally spurious conclusions here, but I think the fact that that some of the adversarial attacks work so well in an end-to-end space probably means that there's a good chance that some of the reverse also works, right? Because clearly there must be some end-to-end signal that is propagating all the way through and that you can get to. Now, whether or not that's going to be like how much, maybe I should put it this way. I don't know how much worse that will be than just having the direct access to the features itself. So I kind of look at this as a trade-off, right? Even with the kind of some of the improvements for like, let's say family and task classification, you still do get a hit for detection. There's other kind of like complexities here. So I think there's a trade-off, right? I kind of look at all these things as like working in a continuum. Right. So like on one hand, if you're in a particular scenario where maybe the tech debt is not that onerous, then probably it is better to just use the features directly. If you're in a state where, in fact, you have an incredible number of models and not enough time to manage them all, then maybe it's an okay trade-off to have maybe slightly less performant model and slightly less explainable, right? I guess that's my thought on kind of the philosophy behind some of this.
Thanks so much. I completely agree, and I like the answer. So thanks.
Okay, really, thank you, Lorenzo, for the question. We have another one from the chat. Antonio, please.
Yeah, thank you, Luca, and thank you a lot, Scott, for the very inspiring talk. It was really fascinating. I have a couple of questions, but let's start with one. So the first one that I have is whether you are considering possible noise that can come up from the task. So whether the kind of embedding that you are learning may be influenced by the malicious or also random noise that you may come up with, or natural noise that you may come up with the stream.
Yeah, that's an interesting question. I don't know that I have a definitive answer to that, but I can kind of tell you what's the top of my head, if that's okay. So I think that the part that's interesting to me about these results was actually the multi-objective stuff, right? So in that case, you have both your natural noise of the vhash, which we already said has all sorts of kind of noisiness, right? Because it's not a perfect match between vhash and goodware, malware, and so on and so forth. So vhash already has some natural noise. Then you have like your labeling noise and your natural kind of just inherent noise that's in the sort of malware detection task data, right? And putting those together, it's almost like in some ways they regularized each other, right? In some case, like, I don't know, that's like my kind of intuition on it, at least, right? Is actually performing better despite the fact that they each have their own completely separate types of noise. And so I kind of look at this as, I think there's an interesting path to go down here where you can start figuring out if there are I think I would call them like complementary objective functions to be including for the malware space, right? Things that either make it more robust because they're completely orthogonal from one another, or that have, you know, orthogonal noise or different noise processes that might affect them, and that they balance each other out. There seems to be some signal there that that's what is happening, but obviously, like, that's a whole bunch of experiments that we didn't get to do.
Okay, thank you a lot, Scott. I will just leave the floor for the others for other questions. So, and then later. Thank you.
Okay,
Sure.
Thank you, Antonio. Since it's already like 5 p.m., I think we're gonna give like time to the last question, and then we can continue like after the recording of the Zoom presentation is gonna over. So if somebody wants to still remain in the Zoom chat, we can still talking a bit if Scott, of course, has time. So,
Sure.
Giorgio Severi, please, the stage is yours.
Hey, Scott, great talk as usual. Very interesting stuff. I was wondering, since these kind of like embedding learning systems tend to improve, like work better with increasing amount of training data, I was wondering if you guys tried to like see what type of improvements you get with like different data sizes. Something like if I train with Sorel instead of Ember, do I get like, you know, 100% better results or something like that?
Yeah, that's a great question. So we are doing some work. So I'll answer your question in 2 parts. One is a more direct answer than the other. So right now we are doing some work on transformers that is straight on exactly the question you're asking. So we did some stuff with Ember. We're now moving up to Sorel, and for those that don't know, Sorel is like a much larger data set. It's like nearly 20 million files, I believe. And so, you know, much larger, a lot more information for the networks to soak up. I actually do believe, based on what we've seen in the transformer space, that yes, if even with this sort of simpler feed-forward network, maybe with slightly different parameterization, there would be, I think, even more improvement. One interesting thing, though, as part of the sort of extended work that I talked about in that final slide of the results, we actually did do like a transfer experiment between Ember and Sorel, where basically we trained on all the Ember stuff and then transferred to different tasks in Sorel. So Sorel itself also has like its own separate type task, not related to the type of type labels that we created. And in fact, we did really well there. I believe it did almost as well, or maybe even a little bit better than the original Sorel papers work there. So again, like there's some really interesting things happening here. I don't know that I have like in my mind like the full picture of, you know, because the transfer is interesting. The transfer to a much larger data set that's actually not even in the same time range. I believe there may be some overlap in time, but most of it, I believe, of Sorel is later than Ember. So I think there's like a lot of really interesting things to explore there. I just don't know if I have like a complete picture of exactly what it looks like, but I think you're right. I think larger data sets and kind of really exploring, I think diving into a little bit more about the makeup of the data sets also is like really interesting kind of fruit for, you know, low-hanging fruit for like future work, I think.
Thanks.
Okay, so thank you for the question. Since we're like a bit late, we're gonna now close the live streaming event. So again, thank you, everybody. Thank you, Scott, because it was very nice talk. And see you again in the next episode. For the ones that want, to still discuss, if of course Scott has time, please just stay in the Zoom call.